today is Thursday, the 16th of April. Okay, so we just got done talking about all the stuff we're going to talk about in Chapter 3. Vertical and horizontal asymptotes, and specifically was the last section. So now we're going to head on over to Chapter 4 and start with Section 1, exponential functions. Okay, so we've been dealing with polynomials most for the first 3 chapters, but now we're going to deal with an exponential function. So this is an exponential function. Looks like this: f of x equals a to the x, where a is a positive number and a is not equal to 1. Okay, so notice that in an exponential function, let's see if I can. In an exponential function, our variable is in the exponent, whereas in a polynomial, we might have it's x to the n plus a n minus 1, x to the n minus 1. The x is the number with the exponent. Now the variable is in the exponent. Alright, so we're going to just start talking a little bit about this, and the best way to start doing this is to start talking about this is to evaluate exponential function. So its domain, so I should add domain is negative infinity to infinity. You can put any x in here and you will not have a problem. Alright, so evaluating exponential functions. So let's evaluate first f of x equals 3 to the x minus 2. Okay, so it's not, I know I said here it's functions where it's a to the x where a is positive, so 3 is definitely a positive number. But x minus 2, you can put functions up here. So like x, or you could put x squared, you can put whatever sort of x you want. Or whatever, you know, I could substitute and say y equals x minus 2, and then this is going to be 3 to the y, and it takes that form. Okay, so anyway, we're going to talk about evaluating this function. We want to know, find f of 4. So what happens when I plug in 4 for x? Well, f of 4 is equal to 3 times 4 minus 3 to the 4 minus 2, which is equal to 3 squared, which is equal to 9. Okay, what about, so g of x, another example, g of x equals negative 2 times 10 to the x. Find g of negative 2. Okay, so this is the exponential function right here. This is just a number being multiplied by it. Okay, so this is going to be negative 2 times 10 to the negative 2. So remember, a number with a negative exponent, a number being taken to a negative exponent is the same thing as 1 over 10 in the positive exponent. Okay, so don't think of it as a negative number, think of it as a small number. So this is going to be negative 2 over 100, which is negative 1 over 50, which is negative 0.02. The only reason it's, if it were just 10 to the negative 2, it would just be 1 over 100. The only reason it's negative is because of this negative 2 out front here. Alright, lastly, let's talk about one more. So f of x, capital F of x this time, equals 4 to the x. And they want to know, find f of 3.2. So that's going to be 4 to the 3.2. And this one you got to use a calculator. So this one's equal to about 84.44. Okay? And actually I want to do one more. So what about h of x equal to 1/9 to the x power. Find h of negative 2 or negative 3 halves. So we have to jog our memory about how do fraction exponents work here. So this is going to be h of negative 3 halves is equal to it's going to be 1/9 to the negative 3 halves. So this, remember, this can be written as 1/9 well, first we can rewrite 1 over 9 as 9 to the negative 1 power. Right, because by definition that's just 1 over 9 to the first power. So this is 9 to the negative first power to the negative 3 halves. And then I have an exponent to an exponent, so this is going to be 9 to the positive 3 halves, which is equal to this is the same thing as equal to 9 to the 1/2 cubed. Because usually we go from, if I have a number to a power and then to another power, I can multiply these two numbers. If I have a number to a fractional power, I can split them up, just going the other way there. So this is going to be 3 cubed, which is equal to 27. Okay, so I know we talked about exponents a while back, maybe at the start of the class, a couple weeks ago. But we might have to, we're going to jog our memory on exponential functions here. Okay, so let's go over some rules that we can use with exponents. So, rules of exponents. And you've already seen all these. We already talked about this, but I'm just going to go over them again. So a and b greater than 0. Then we have a to a number x times a to a number y equals a x plus y, right? So if you have the same number to one exponent times a number to another exponent, or that same exponent, it's you can add them together when these two numbers are multiplied. So an example is 2 squared plus 2 cubed is equal to 2 to the 5th. Alright, so what about for any number, a to the 0 power is 1. Okay? And that rule I just, so example, none needed here. Okay, because any number to the 0 power is 1. Alright? The rule I was just talking about, a to the x to the y is equal to a to the x times y. Okay? An example here would be like 2 squared cubed is equal to 2 to the sixth. Okay, another one we've seen already is a times b. Two different numbers to the same exponent is ax times bx, b to the x. Okay, so here we could do 2 times 3 to the 4 is equal to 2 to the 4th times 3 to the 4th. Okay, this you can do the same thing with division. So, so this one, these two kind of go together because it's a to the x instead divided by a to the y. So this is going to be a to the x minus y. So example, 2 squared. Oh, I messed up here too. This should be not a plus, but it should be a multiplication. 2 squared divided by 2 cubed is equal to 2 to the negative 1. Okay. Alright, so, and then a to the negative x is equal to 1 over a to the x. And notice this can be written as 1 over a to the x, since 1 to the x, 1 to any power is just 1. So this part here is really equal to 1 to the x over a to the x. And then you can use this rule here. You're using this guy. Oh no, not this, not quite. It's this one here. Right, because to use this rule, you need the two numbers to be the same number. And 1 and a might not be the same. Okay, so we're almost done here. So with our rules, so you really just need to remember a to the negative x equals 1 over a to the x. Okay, last but not least, we have a over b to the x is equal to a to the x over b to the x. That's the one I used here. Okay. So there are the rules of exponents, and I'll be using these quite a lot in the next couple examples. In fact, these next examples just a couple ways to use them. So they want you to simplify 6 to the square root of 27 times 6 to the square root of 12 and 6 to the root 3 to the root 3. Okay, so for the first one here, we got to look at our rule sheet. So it looks like we've got two numbers, 6, two of the same number, 6, being raised to two different exponents, and then they're multiplied by each other. So that kind of looks like this example here on our rule sheet. Because a would be 6, x would be the square root of 27, and y would be the square root of 12. So we're going to use the fact that this is equal to 6 to the square root of 27 plus the square root of 12. Okay? So now we want to simplify this exponent here. So I'm going to write this as 6 times, it would be the square root of 3 times 9, that's the same thing as 27, plus the square root of 3 times 4, that's the same thing as 12. Okay, so this is equal to 6, and the square root of 9, okay, so I'll do this in two steps here. So this is the square root of 9 times the square root of 3, plus the square root of 4 times the square root of 3. So this is equal to 6 times 3 root 3 plus 2 root 3. which is equal to 6 to the 3 root 3 plus 2 root 3 is 5 root 3. And then this is going to equal, right, now I'm using, so 6 to the 5 times 3, I'm going to use this power rule in reverse. So I'm going to say, well, 6 to the 5 times root 3 is the same thing as 6 to the 5 to the root 3 power. So this is going to be 6 to the 5 power to the root 3, which is 6 to the 5th power is 7,776 into the root 3. And then on this one, you can use your calculator. Okay, so that's how you simplify the first one. So on the back here, let's go ahead and simplify the other example. So we have 6 to the root 3 to the root 3. So again, we're going to use that power rule. So that's going to be 6 to the root 3 times root 3. The square root of 3 times the square root of 3 is 3. So this is 6 to the 3rd power. 6 times 6 is 36. Times another 6 is 216. So that's how you would simplify those two. Okay, so moving on. So now we're going to talk about graphing exponential functions. Okay, graphing exponential functions. We're going to start out with the method, before we would talk about just graphing functions by just making the x table and the y table. And then we learned about finding x-intercepts and y-intercepts. And then for rational functions, we learned you have to find horizontal and vertical asymptotes and use all sorts of tests to make the graphing easier than just graphing a bunch of random points. But graphing a bunch of random points always works. So we're going to start off by doing that. So f of x equals 3 to the x. So we want to graph that one. So we're going to make our table here. So let's go ahead and get some x values and some f of x values. So if I put in -3, well, 3 to the -3 is 1 over 3 cubed. So this is 1 over 27. 3 times 3 is 9, times 3 is 27. So I do -2. 3 to the -2 is 1 over 3 squared, so that's 1 over 9. -1 is just 1 over 3. 0. Any number to the 0 power is 1. If I do a couple more here. So 3 to the 1st power is 3. 3 to the 2nd power is 9. And 3 to the 3rd power is 27. So you see this, as I move from left to right, I have numbers that are, so the further I go left, these numbers seem to get closer and closer to 0. And the further I move right, the numbers just start to blow up and get very large. So the way this graph looks is so here's -3, -2, -1. So they're all kind of really close to 0 here. 1/3, and then 0, 1. Then you go up to 3. 1, 3. And then all the way up here, so it's gonna look kind of like this, and just grow super fast. Okay, so you might have seen this. So actually, human population models often follow an exponential curve, because the more or animal populations in general. There's a bunch of things in nature that follow an exponential curve. for example, infectious diseases usually follow some sort of exponential curve at the beginning, and then they will flatten out as they reach the peak of their of hosts they can infect. Okay, so now let's draw another one. Let's do instead. We're going to change up what a is. So we're going to change a to a number greater than 1. It's going to be 1/2. It's the x power. So now, if I make my table here, we get x, f of x. So we get a -3. Start at -3 again. So this is going to be 1/2 to the -3 power, which is this is going to be, so remember this is 2 to the -1 to the -3. So that's equal to 2 to the 3, which is equal to 8. Okay, so I just use my exponential rules there to rewrite that. So now if I do the same thing, I get 1/2 to the -2. Same steps here. This is going to be 4. -1. So 1/2 to -1. Well, that's just going to be 2. 0 is 1. 1. So 1/2 to the first power is just 1/2. 1/2 squared is 1/2. So squared. So that's going to be 1 squared over 2 squared. Another exponential rule there, which is just 1 squared is 1, so it's 1/4. So this one's going to be 1/8. So since this a value is in between 0 and 1, and this one here is in between, this one's greater than 1. So let's see, remember we're only talking about a values that are positive. So let's see how that changes our graph. And we can already see how it does by the table, because in this first table, the negative numbers were the numbers that got you really close to 0. But here in this table, the negative numbers give you the larger numbers. So it's almost like a flipped version of this graph that we drew in our first example. Instead, now we're going to have at 1, 2, and 3. Here we have an 1/8, so that's all the way down here. Here we have a 1/4, a little bit bigger, and then here we're up to a 1/2. And then 0, we're up to 1. And then at 1, we're up to 2, 3, 4. And then at 2, we're up to 4. And it goes on and on. So notice that in this function on the left here, or on top here, this is 3 to the x. So a is greater than 1. In this function, this is going to be 1/2 to the x. So a is in between 0 and in between 1. So, and if the two differences here is the fact that we have, when you have a is greater than 1, your graph increases from left to right, and when your a is in between 0 and 1, the graph decreases from left to right. So when a is greater than 1, we call a the growth factor. So 3 would be the growth factor, because our graph is growing by a factor of 3. Here we would say if a is in between 0 and 1, this is going to be the decay, or the decay factor. Okay. So those are important to remember. If a is greater than 1, you're going to have your exponential function is going to be increasing. And if a is in between 0 and 1, your exponential graph is going to be decreasing. So remember before, like for example, when we talked about linear functions, ax plus b, or mx plus b, if m is positive, then the slope is positive and you have an increasing function. If m is negative, you have a decreasing function. So here, same idea, except in exponential functions, it matters what your a value is. Alright, so let's continue. So some other things you need to know about of exponential functions is we already talked about the domain is negative infinity to infinity. Right? You can plug in any value. Without dividing by 0. Taking square root of negative numbers. And so yeah, there's no problems with any sort of x that you can plug in. However, the range is going to be 0 excluded to positive infinity, because no matter what x you plug in there, you're never going to get a negative number, because remember, we're only talking about a is positive. Okay, so so this is all for y equals a to the x. Okay, so we're going to talk about some variations here of this. So the range is going to be 0 to infinity. There's no way I can plug in any value x and get 0 back for y, because even if I plug in 0, a to the 0 is 1. If I plug in a number very, very close to 0, there's no value that gives you a 0 back in an exponential function. Okay, but you can get any positive value since a is positive. Okay. So we talked about the growth factor and the decay factor. So the next thing we need to know, the graph. So f of x. So we talked a little bit about this when we talked about talking about functions. F of x is 1 to 1. So for every x value, there's only one y value. F of x is 1 to 1. So every x value has one y value. So some examples of functions that are not 1 to 1 would be like y equals x squared, because negative 2 and positive 2 both map to y equals 4, but it's still a function. So this one is 1 to 1. So you know, there's only one x value that gives you that y value back. So in other words, it also has an inverse. So the graph, another one is the graph of f has no x-intercepts. So that's, remember, sorry, I should write this as f of x. That's only if it's in the form a to the x. We're going to introduce some ways you can modify these exponential functions. But for this particular f, we have no x-intercepts. And the points negative 1, comma 1 over a, 0, 1, and 1, comma a are on the graph. So, like in our example here, a was 3, so 1 over a, negative 1 and 1 over a, that's this one, 0, 1, and 1 and a are on the graph. The x-axis is a horizontal asymptote. And Yeah, that's all we need to talk about for now. So those are some things you can notice about this function, f of x equals a to the x. All right, so now we're going to talk about transformations. Of f of x equals a to the x. So if you want a vertical shift, we would, so this is if c is greater than 0, then f of x equals a to the x plus c shifts up by c. And f of x equals a to the x. So I'm going to call these y. Minus c. Shifts, I'm going to say shifts f up. So it shifts the function f. Shift f of x up by c, and this one shifts it down by c. Okay, so horizontal shift, if you had y equals a to the x minus c, shifts to the right by c. Y equals this diagram was also on page 427 in the textbook. Y equals a to the x plus c shifts to left by c. So reflection, horizontal. Reflection. So a reflection, y equals negative a to the x, or y equals a to the negative x. So this is going to give you reflection about x-axis. This one's going to give you a reflection about y-axis. Okay, and then vertical stretching or compressing. So if you did y equals ca to the x, so that stretches the graph or compresses it. So stretch vertically stretch if c greater than 1, shrink if 0. Okay, and then we finally have a horizontal stretch. Okay, so that's going to be y equals a to the c times x. So stretch, wait a second. it actually shrinks. It's the opposite here. Shrinks if c is greater than 1 and stretches if 0 less than 1, less than c less than 1, if it's in between 0 and 1. Okay, so now that we've got that table, and again that table's on page 427, we are going to do some examples about graphing some other functions. So we're going to graph first we're going to graph y equals 2 to the x. Okay, so that's going to be, remember our points -1 and 1 over a, 1/2 are on the graph. 0, 1 is always on the graph. And 1, comma a are always on the graph. So it kind of connects going like this. Okay, so that's our graph that we're going to use for translation. So now they ask us first to graph y equals 2 to the x plus 2. So that's vertically shifting our original graph. So to draw this graph, we just need the 3 points. Everything gets moved up by 2. So instead